Hello and welcome to this e-learning module on proper implementation of ancillary protection functions for prevention of inadvertent trippings in substation. In this module, we will discuss about the implementation of some of the important ancillary protection functions of transmission line distance protection series. For example, we will discuss about the implementation of SOTF, Stub, VT fuse failure, broken conductor, power swing blocking, and the auto-reclosure cycles. We will discuss about the concepts of these ancillary functions, that is SOTF, Stub, VT, fuse fail, broken conductor, PSB, and auto-reclosures. Then we will discuss how to implement these functions in Siemens numerical protective relay, that is 7SA522, and also P444 or 442 of Alstom series. Basically, we will discuss that what precautions we must take while implementing these ancillary protection functions at our substation. We will discuss about these implementations by using some simple schemes or some sample schemes of one of the substation, and then we will discuss how to take care of some of the common mistakes that we generally do while implementing these ancillary protection function. So hopefully at the end of this learning module, you will be able to understand the concept of SOTF, stub, VT fuse failure, broken conductor, power swing blocking, and auto reclosure. As well as I hope that at the end of this module, you will be in a better shape to understand the different parameters of the 7SA5221 relay and P444 or P442 Alstom make numerical distance protection relays regarding these ancillary functions. So now let us start with our first topic, that is the implementation of SOTF protection function. So now, as the name suggests, SOTF is basically switch on to fault. So we are switching on our circuit breaker onto a pre-existing fault. So generally this kind of problem we encounter during energization of a transmission line onto a forgotten earthing. So it might happen that transmission line, suppose between two substation A and B, was taken for shutdown or was under shutdown for some maintenance work, and some local earthings were used at different locations. Now in the evening or after the completion of work, when we are energizing these lines, suppose out of there's n number of local earthings, one or two earthing remains intact, or we forgot to remove those earthing. So now this is a permanent fault, permanent three-phase fault on the transmission line, and we are trying to close our circuit breaker onto this existing fault. So it might happen that during this time, when we are closing the circuit breaker onto an existing dead three-phase fault, it happens that voltage might not build up. So voltage will not build up. At the same time, there will be large current flow because of this short circuit path. So since the voltage doesn't build up, so the directional element of distance protection, that is the directional measuring element, that cannot operate correctly because it depends upon the voltage polarization. At the same time, since we are having a large current magnitude, so we can enable a protection function which depends upon the flow of current only. So basically what happens, a protection function which enables after the CB closing command is given. So just when we are giving a CB closing command, after that, for a particular window, that window is called the seal in time. So suppose the seal in time is 200 millisecond by default. So within this 200 millisecond, if suppose suddenly a current increases beyond the set limit, then our protection function must recognize this as a switch on to fault, and it should issue a three-phase trip command immediately. So now if you combine all of these features in one, what happens is basically SOTF is CB closing command is given. Then from this CB closing command to some 200 millisecond of seal in time, current increases. So this is an overcurrent based protection. and then it will issue 3-phase trip command. Another important thing, how much time should it wait? As you can see, this is a permanent 3-phase fault pre-existing on the line, so the time of operation should be instantaneous. So SOTF is an instantaneous overcurrent based protection which starts after the closing of circuit breaker till a ceiling time period of 200 milliseconds. In some relay, we are using the impedance based SOTF protection also. One of other important thing is that you cannot say that the earth switch is we forget to remove the earth switch only in the lines, but we can forget to remove the earth switch even at our substation end or our local end. So the SOTF must be a non-directional protection function. So SOTF is non-directional instantaneous overcurrent protection function which starts after the breaker closing command is given. So now how do we implement in case of 7SA522 relay? So before this implementation, just look at, since there is no scheme drawing, but suppose that we are having a scheme drawing in which one binary input, suppose binary input 7 is used for CB closing command. So now we can have two different scenario. We can have 1.5 CB scheme and we can have DMT scheme. So in case of 1.5 CB scheme, we can energize the line either through main CB or through tie CB. In case of DMT scheme, we can energize the line either through main CB or through transfer bus CB, but only one at a time. Then another thing, what is the meaning of this, that we will discuss separately in some other module, or some module might be available on this Pragyan portal wherein someone have discussed about this DMT and 1.5 breaker scheme. But now for the time being, let us consider 1.5 CB scheme. So now in the 1.5 CB scheme, the closing of circuit breaker can be through two different modes. So you can close the circuit breaker either through TNC switch, or we can close the circuit breaker through BCU. So we can have a closing command through this BCU output. At the same time, we can have a trip normal close switch, and then this ADC positive, this will be extended to the closing coil of circuit breaker. Suppose this is negative. So this is for main CB. Likewise, we can have for tie CB also. So this can be the tie CB scheme. So this is suppose main CB, this is suppose tie CB, and again this ADC positive, this is the closing coil of tie CB. Now the important thing for the BCO, you need only one binary input for detection of CB closing command. So what we do generally, now we can parallel these two, that is we can parallel these two, and then we make one single input, that one single output. So this negative then will be from here, and it will be connected to one of the input of BCU, and the negative will be given here. So whenever out of these four conditions any one condition happens, then the binary input of the BCU gets activated. So now how do relay detect that you have charged the line or you have closed the line? So in the Siemens relay, this is done through this input manual close detection. This is available inside power system data 2, and you have to map this input 7 for active with voltage, that is H. Once you map this, so whenever we close the circuit breaker either through BCU or through TNC switch, any breaker, main CB or tie CB, then this manual close BI7 will get high, and that will activate this manual close detection, and that will activate the SOTF protection function for next 200 millisecond. After this, the important thing is that how to set. So the setting of SOTF protection function is very simple. You have to just enable this SOTF protection function and set a current magnitude as per your requirement. In PowerGrid, presently it is set as 1.5 ampere for 2000 or 3000 ampere city ratio, and 2 ampere for 1 ampere city ratio. So you can see this in template also. So now once we set this our current stage for SOTF protection function, the next step comes is what should we select. Do you want to have only overcurrent, or do you want to have SOTF protection for impedance also? So in the Siemens relay, it is available in this tab, that is instantaneous tripping after SOTF through zone 1B. Once this is done, the one more thing that is important is the recognition of line closure. That is how this Siemens relay detects where you have energized the line or not. So there are three possible ways. One is through manual close BI, that I have already explained, the manual close BI. The second thing is through the current magnitude, and the third thing is through voltage magnitude. So if the current magnitude rises above a set threshold, so suppose if you see here, this is the pole open current threshold, which is 0.05. So in case suppose your CT ratio is 1000 by 1, so the pole open current threshold, that is I pole open, is 50 ampere. So now the current thing is that if you see this pole open current threshold, so anytime if when our line is under shutdown, generally this current will be much less than 50 ampere. So it can be 5 or 10 ampere. So once this current is below this ampere, and when you charge this line, when you close this circuit breaker, suddenly the current will rise, so current will increase. Once this current increases beyond 50 ampere, then the relay will detect it as a line closure. Now, after the closure detection, it will wait for this seal in time, which if you see over here, it is 200 millisecond. And if within this 200 millisecond window, if there is an increase of current from this 50 ampere to the set value of 1.5 into 1000, that is 1500 ampere, so our relay will now issue SOTF trip command. Another method is that you can have a voltage threshold. So this pole open voltage threshold, 25 volt. Once the voltage is below this, the relay will detect it as line de-energized condition. Once the voltage rises above this 25 volt, it will detect it as line closure, and then in that case also it can issue a trip command based upon the settings. So these are the implementation in 7SA522 relay. So now moving on to the next topic, that is the implementation of Stub protection function. So now Stub is basically a protection function which is applicable only in case of 1.5 CB scheme. So Stub is applicable only in case of 1.5 CB scheme. Another thing is this stub function, it is activated only when the line disconnector is open. So when your line isolator is in open condition, then only stub protection will come into picture. So if you see, this is our distance relay, and the two input of the distance relay are generally the current, which is connected through the parallel combination of main and tie base CT, and then the voltage which comes from the CVT. So now if you recall the line arrangement, so the first element is LA, followed by CVT, wave trap, or in correct order, LA, wave trap, CVT, line isolator, and then the bay equipments. And if you see this CVT, before this CVT is 89L. So if this 89L is open, so the CVT input will not be available to this relay. And since V is equals to 0, so Z is equals to V by I, it will be always 0, and your distance protection might not operate correctly. And generally it will not operate correctly. In that condition, whenever our voltage is 0, we have to enable one additional function which would depends only on the current magnitude, and that's why stub is also a current or overcurrent based protection which is applicable in 1.5 CB scheme only. And then the next thing, it is applicable in 1.5 CB scheme only. It is overcurrent based protection. It is time delayed, so it is 100 millisecond time delayed protection. Now uh, the important thing, how to implement this stub protection function in case of Siemens relay. So if you see over here, you will be having this 89L isolator status, and this is suppose DC positive, and this is suppose 89L open. This will come as one of the binary input. This is 89L close, and it is connected to suppose one of the binary input of the relay, and this is our negative coil. So Kenley, this is again one of the binary input. It is connected to one of the binary input. Now what happens whenever our 89L isolator opens, this will becomes NC, and once this becomes NC, this positive supply, DC supply will come up to this point, and this binary input gets activated. And once the isolator closes, then this will be open, so no DC voltage will come here, and this will not be activated. So once this 89L opens, we have to enable one protection function, and that protection function is stub protection function. And to enable that protection function, we have to go to the overcurrent, backup overcurrent tab, and then in the backup overcurrent, this address number 7131 is for iStub enable, and just mark this to your corresponding binary input of 89L open. Once stub is enabled, the important thing is the settings. So we have to set only the operating mode, which is active with loss of VT circuit, and then you have to go to this stub protection function and set the time. Suppose this will be available in our template. So this is the implementation of stub protection function in case of 7SA522 relay. Hopefully the implementation of SOTF and implementation of stub protection function as well as their working is clear up to this point. Now we will move to the next thing, which is VT fuse failure function. Basically, VT fuse failure, what happens is that our relay, this is suppose our, this is suppose our relay. So suppose this is my relay, and in this relay there are two input. One is from CVT and one is from CT. So this is current, this is voltage, and relay will calculate the impedance based upon the ratio of the voltage and current. Now due to any problem in the secondary circuit of the CVT, if this voltage input is not available, so V is not available, in that case what happens is that the impedance calculated by relay will not be accurate, or if the voltage is 0 for all three phases, in that case it might happen that the impedance is less than the set value for any zone, and the relay might maloperate. To avoid these kinds of problems, the fuse failure protection is enabled, and basically fuse failure will block the protection function. But how this fuse failure is implemented? If you can remember or recall from the basic fundamental concepts, then in case of any unbalance in the network generates negative sequence and zero sequence components. So unbalance will generate negative sequence and zero sequence. Now what happens? Suppose this is my CVT input for R phase, Y phase and B phase. Suppose out of these three phases, one of the fuse fails. So now there is an unbalance between R and B phase because Y phase voltage is not coming. So you will get negative sequence and zero sequence in voltage. But at the same time, the current of the three phases are balanced. So no negative sequence and zero sequence current will be there. Based upon this magnitude of negative sequence or zero sequence, presence of this negative sequence or zero sequence in the voltage and the absence of the same negative sequence and zero sequence in the current, the relay will identify it as fuse failure. But there is another problem. Suppose all three phases voltage of all three phases, that is the fuse of all three phases fails. In that case, now there will be no negative sequence or zero sequence generation because this is again balanced. So the second method that is being used by the relay manufacturer is memorized voltage. So it will determine the voltage memorized just prior to fault and voltage at the fault point. So voltage after fuse failure. Similarly, it will check the memorized current and fault current. Generally, if it is a fuse failure, so there will be a change in voltage magnitude, but there will be no change in current magnitude, and the relay will determine or declare it as a fuse failure. Once relay detects it as a fuse failure, it will block the protection function. Fuse failure supervision is generally blocked for 200 milliseconds following any line energization, because if you are closing the circuit breaker poles, so generally it might happen that all three poles of the circuit breaker might not close simultaneously. There might be some closing gap or closing difference between the three phases. So now in order to cater those closing time delays between the poles, we generally block fuse failure for 200 milliseconds after every manual closure. Now, the settings of fuse failure is very simple. In case of Siemens relay, there are some settings like per template, and you have to only implement those settings. But the important point is here this voltage failure supervision. It is through current supervision. So what does this mean? This means that this relay will check the pole open current threshold again, and if this current magnitude is less than the pole open current threshold, so suppose the current flowing through the line is 60 ampere and my CT ratio is 2000 by 1. So now this pole open current threshold is 100 ampere and the current flowing is 60, which is less than 100. So in this case, what happens? Relay will detect it as line under de-energized condition, and if in this condition fuse fails, it is not going to block the distance protection, but it will issue a trip command. So this is the limitation of Siemens relay. Similar limitations is also there in case of MyCom and REL670 relay also. Now broken conductor. Broken conductor, like the fuse failure, is again the same. There will be, suppose there are three conductors, R phase, Y phase, B phase. So IR, IY, IB is there, and suppose out of these one conductor breaks, so suddenly you will get, suppose, close to zero current in this, but normal current will be flowing through these two. So now in this case there is an unbalance in current, but there will be no unbalance in voltages. So the relay will determine the zero sequence current magnitude if it is higher than some set value and the zero sequence voltage is less than the some set value, then it will detect it as a broken conductor. And in case of broken conductor, there is no tripping at present in power grid. There is only an alarm. Some manufacturer uses the concept of I2 by I1, that is negative sequence by positive sequence current ratio, and some other uses the concept of phase current minimum by phase current of maximum among the three phases. This concept of minimum by maximum is used in 7SA522 relay of Siemens, while the second concept is used in P444 as well as in REL670 relay. So now we move on to the next topic, which is power swing blocking. Power swing, it is basically started by sudden load change. Sudden load change anywhere in the network due to a fault. Close to the center of the power swing, there is low voltage and thus low impedance will occur. So close to the center, if suppose this is your power swing. So now if you see within this region, there is a dip in voltage. So once there is a dip in voltage, and likewise there might be the change in current magnitude. For this region there might be some change in current magnitude, and then it will be normalized. So this is the current magnitude. Voltage magnitude is also changing, so you will get change in impedance. And it might happen that due to this change in impedance, this impedance might reach inside the zone boundary and relay might operate incorrectly. So the distance protection relay must be blocked during the power swing. This can be done by measuring the transit time of the impedance locus passing two dedicated impedance zones. So you can calculate by this. Suppose this is my zone boundary, this is simple zone 1. So I can draw two parallel lines like this. The time to locus to traverse from one point to another. Suppose the locus is traversing like this. Sorry. So suppose my locus is traversing this path, and now you are drawing two parallel lines. So the time to traverse this point to this point, if it is more than a set time delta t, then it will detect as a power swing. Because generally what happens, for a fault, your impedance will quickly move from this point to this point. But for power swing, it will move slowly from this point to this point. So to cross any 2 points. For fault, it will take less time. Delta T is very less. For power swing, delta T will be more. And on this basis, simply the relay will detect power swing. When power swing detection operates, any impedance zone can be selected to block or not as required. Presently in PowerGrid, we use the philosophy of block all zones. In some regions, we are using block all zones except zone 1, but generally block all zone is being used. Next, autoreclosure. So autoreclosure is generally accepted practice of EHV transmission lines because most of the faults on the power system networks are LG faults. So most of the faults are LG fault, that is single line to ground fault. And these single line to ground faults are generally transient in nature. So once the breaker is opened, so after some time if we close the breaker, then it is possible that the breaker will successfully close and line will be energized. So by this way you can minimize the outage time also. So generally in case of single line to ground fault, what happens is that suppose there is a these are the three poles R, Y, B, and there is a fault in R phase to ground. So this is Rn fault. So what happens is that we will open R phase breakers only. Remaining two breakers will remain closed, and after certain time delay, this breaker will be given a closing command. And this certain time delay is called dead time. So there are many types of autoreclosure schemes. Presently in PowerGrid, single phase high speed autoreclosure schemes are being used, and this is basically single phase single shot autoreclosure. Now again, what that particular time during which your breaker pole is open is called dead time. So after the elapse of this dead timer only, we can give the closing command. So auto-reclosing requires a dead time which exceeds the deionizing time. Deionizing basically is the suppose whenever we give the opening command to our circuit breaker poles. So once we give the opening command, your moving contact separate from the fixed contact. So suppose these are the fixed contact and this is the moving contact. So this moving contact separate from the fixed contacts, and once this contact separates, there will be some arc here. Once this arc is formed, so you have to quench this arc. Now to quench this arc, SF6 will come inside this space to quenching the arc, and once the arc is quenched successfully and sufficient dielectric strength is maintained over here. So what is the meaning of sufficient dielectric strength? That is your moving contact should get separated sufficiently from the fixed contact. So once the moving contact is sufficiently separated from the fixed contact, then the dielectric strength over here is more than the re-striking voltage. So the general principle is that rate of rise of re-striking voltage must be less than the rate of development of your dielectric strength. So rate of development of dielectric strength. And if this condition satisfied, then your arc will be successfully quenched. And this dead time is generally in PowerGrid it is set as 1 second, and this will depends upon various factors like the voltage level, the speed of the breakers, type of the breakers, and the capacitive coupling between the adjacent conductors, as well as the fault duration, wind conditions. So there are multiple factors on which it depends, but generally in PowerGrid we select it as 1 second. Then reclaim time. So now once the circuit breaker has closed after 1 second, that is after dead time. So now if there is any fault from this 1 second to next 25 seconds, so that 25 second is called reclaim time. And if within this time there is any fault, then all three poles of circuit breaker must open. And why it is done is that suppose you are having any circuit breaker, you are having a spring or spring pneumatic circuit breaker. So we are having a spring or spring pneumatic circuit breaker. In case of any of these two circuit breaker, what we have generally is that you are having a mechanism. So once breaker opens and then it closes after dead time. Your mechanism needs certain time for suppose energization of spring or spring charging, also for developing the air pressure inside the circuit breaker. So these things need some time, and only after your spring is fully charged, your air pressure is fully maintained, then you can go for the next cycle. So this time is called reclaim time, and generally if reclosing shot has been carried out and line is energized, a new fault occurs before the reclaim time has elapsed. The auto reclosing equipment is blocked and signal for definite tripping of the breaker is obtained. After the reclaim time has elapsed, the auto-reclosing equipment returns to the starting position and a new reclosing sequence can occur. Reclaim time must not be sent to low value that the intended operating cycle of the breaker is exceeded when two faults incident occurs close together. So now we will discuss about this. So as per this IEC publication, all breakers should follow this duty cycle. What is the meaning of this duty cycle is that all breakers are always should always be ready for one open operation or one trip operation. Once it opens or once it trips, then after a minimum time of 300 millisecond only we can close the circuit breaker, but generally in power grid we are using 1 second at that time, so this is not a problem. So only after this 300 millisecond or in power grid 1 second we can close the breaker. Once we close the breaker, then if there is a permanent fault then it will open, and now we can close the breaker only after 3 minutes. This is the maximum time that we can have. Generally in power grid we are using this as 25 seconds. This is the reclaim time. After 25 seconds, now we can close the breaker again, and then the cycle repeats. So now if you see here, this is an image taken from Google. So this suppose is a protection function. Once a protection function detects a fault and it operates, so this is the operating time of the protection function. Once the protection function operates, it will energize the tripping coil of the circuit breaker. Once the tripping coil is energized, your contacts will separate. So once the contact will separate, then arcing will start, and after some time arc will be extinguished. Once arc is extinguished, the contact will be fully open. So now the contact is fully open, your protection resets, and from this point the contact fully open, your dead time starts. So once the dead time is finished, so after the elapse of dead timer, the closing circuit is energized through the closing command. The breaker will make the contacts, and contacts will be fully closed. So now if there is another second fault, suppose there is a second fault at this point of time, so what happens is that now the breaker will see the second fault within this reclaim time, so it will issue a three-phase trip command and breaker will go into the lockout mode. So this is the basic of the auto reclosure. So generally in this session, we have discussed about some of the ancillary functions which are most important for distance protection, like the SOTF, stub, VT fuse failure, broken conductor, power swing, and in the end, we have also discussed about the autoreclosure. We have discussed about the implementation of the SOTF, stub, VT fuse failure in Siemens 7SA522 distance protection relay. We have discussed about some of the settings like the pole open current threshold, like the settings of SOTF function, how what settings we have to implement, why we are implementing only some particular settings, what are the limitations of the current only mode, current voltage only mode, how the binary inputs are configured. So we have discussed all these things in this session. Hopefully the concepts which are explained in this module is clear, and in case of any doubt you can always comment in this discussion forum, or you can directly mail to my email ID and I will try to reply to all these queries. So we will close this learning module at this point only, and uh, thank you for watching this module. Thank you.